This talk is related to nuclear waste disposal in clay shale, which is a favorite host rock also in Switzerland and many other places. When you build a repository, which typically is at the depths of 400 to 700 or 800 meters below ground surface, the excavation at that depth in this material causes the formation of damage in the host rock, and the damage includes formation of excavation parallel fractures. And many people have studied the formation of these fractures in this excavation damaged zone, which is also called EDZ, and have created models. And one of the important properties of this EDZ is that you have a significant increase in hydraulic conductivity. For example, when you measure hydraulic conductivity in radial boreholes from a drift, by several orders of magnitude, and this of course can have negative impacts on the long-term safety of such a repository. This is a model which has been established based on investigations in an underground research laboratory in Switzerland, which is called the Monterey Underground Research Laboratory. And this model of the EDZ includes extension fracturing, which are these tangential fractures, which you can see here. Also includes bedding plane parallel slip. Bedding in this underground rock laboratory dips with about 45 degrees towards south. And what you can also see in this model, that the fracture frequency is initially high when you are close to the excavation boundary and diminishes as you go away from the excavation boundary. This model assumes a anisotropic but homogeneous material. In the project that I'm going to present here, we want to consider explicitly the role of geological heterogeneity, and we want to understand what are the impacts of geological heterogeneity on the geometry and on the properties of the damage induced by the excavation, and we want to study this in an in situ experiment at the scale of 1:1. So 1:1 means it's also relevant for the scale of a real repository drift, and we want to study this damage process in 3D space and in time. This is the location of the Monterey Rock Laboratory. Some of you have already been there. It's really a good place to go and see a lot of great research projects. This is not a site where waste could be stored in the future. It's a pure research site. The laboratory has been constructed from an existing highway tunnel between points 1 and 2, and the tunnel crosses a small mountain in what is called the Jura Mountain, a hilly fold and thrust belt. Here you see a plan view of the underground research laboratory. So this is again the highway, and here you see a lot of underground excavations, and within the excavation and from tunnels and the boreholes drilled from these excavations, a lot of experiments have been carried out. This figure here in the center is a detail of this southern corner. And here you see where we have carried out our experiment. It's called the EZB experiment, which included the excavation of a small tunnel, which is called the EZB niche. You see here the dimensions of this EZB niche, which are relatively close to the dimension of a real repository drift, which today in Switzerland has a diameter of about 3 meters. This EZB niche or tunnel was excavated in this direction, and this direction is normal to the strike of bedding of this clay shale, and the dip of bedding is 45 degrees towards south. Here you see a zoom photography of the opalinus clay. It's an old Jurassic strongly over-consolidated shale with a water content of about 6%. And you also see that you have a bedding. The spacing between bedding planes is very small. Yeah, it's in the order of a few millimeters. The material therefore has a strong, let's say, what we call matrix anisotropy in terms of elastic properties. So you see Young's module parallel to bedding is 10 gigapascal, perpendicular is 4 gigapascal, but also in terms of strengths, you see the unconfined compressive strengths parallel and perpendicular to bedding is also strongly different. In addition to this, let's say, primary properties of the matrix, we have other pre-existing geological or tectonic structures, which are bedding parallel shear zones. These are called the south-southeast dipping shears. They are not easy to see in the tunnel because they are normally very thin, only a few millimeters thin. So it's not really easy to see them, what is shown here as a blue line in the field, but they are bedding parallel. In addition to these bedding parallel shears, you have what we call south-southwest dipping shears. So they dip with a smaller dip angle in a slightly different direction, and also these south-southwest dipping shears are normally very thin and not so easy to see in the field. So these are important heterogeneities which have a big impact on, let's say, the detailed geometry of damage and fracturing in the EDZ. Our experiment included 3 stages: a pre-excavation stage where just an entrance to the future tunnel was constructed, and from this pre-excavation stage we drilled a series of boreholes to characterize the conditions prior to the excavation of the niche in terms of structure, in terms of damage, and also in terms of pore pressure. Then we had the excavation of the niche, which occurred in several stages. One stage lasted 1 to 2 days and included the excavation of something like 0.5 meter to 1 meter length of the niche. And we did a lot of mapping and monitoring during the thin excavation stage, and then the post-excavation stage, where a lot of radial boreholes were drilled into this EDZ in 2 vertical planes, but also a series of boreholes were drilled in horizontal direction through the tunnel face at the end of excavation. Here you see a little bit a cartoon how things progressed in time. This happened in the year 2005. So these are pre-excavation boreholes drilled to monitor pore pressure, drilled to characterize geology and structure prior to the excavation. Then you have a series of excavation steps, always with detailed characterization of the structures visible in the excavated surfaces. And then you see the post-excavation boreholes drilled into the final tunnel face and also drilled in radial direction in 2 profiles through the excavated niche. What did we observe? First, we looked into the entrance. This is just the entrance to the niche, and in this side walls of the entrance, in the west wall and in the east wall, we could already map a lot of important structures, and these structures were not related to the construction of the EZB niche, but to the construction of what is called Gallery 04. So this is Gallery 04. So you see on the west wall, you see again bedding, and you see bedding parallel shears. So this is the pre-existing, let's say, inventory of structures, and a similar inventory you can see on the east wall. And then you see the induced damage, which includes 3 types of fractures. So very shallow fractures, which are parallel to bedding, and then tangential, semi-tangential fractures, which are not very much expressed. They might have formed directly close to the face when Gallery 04 was excavated. And then you have the red set of excavation-induced fractures, which are perfectly tangential or parallel to Gallery 04 tunnel axis and which are the main structures. Now these structures, as you can see, form mainly in a direction orthogonal to these bedding parallel shear planes. And it was one question how they would form, what would be the main cause. So one explanation for the cause of these red fractures was given by comparing the fracture pattern with modeled stresses. And this is a relatively simple stress analysis because it's based on 2D models, created normal to the gallery 04 for various assumptions. So in this diagram, you see an assumption where we just have isotropic or anisotropic matrix properties, but without any tectonic structures. So you see that you have concentrations of deviatoric stresses close to the invert of the tunnel. You see that there are some differences in the lines of deviatoric stress contours between the isotropic on the left-hand side and the transversal isotropic elastic model on the right-hand side. And you see, let's say, a similar behavior on the east wall. So this difference from these two diagrams is just caused by changing the property of the matrix. Now, if we include bedding parallel shears, we have a strong change of the calculated deviatoric stresses because most of these bedding parallel shears have been reactivated in shear in response to the excavation of gallery 04. When we add in top of the bedding parallel shears the south-southwest oriented shears, we again see strong modifications of the initial stress field. So these reactivated tectonic shears have a strong impact, maybe not only on the stresses that evolve around the tunnel, but also on the induced fracturing, because most of these fractures that are shown here in red, in fact, can only form because of slip along the bedding parallel and also non-bedding parallel shear zones. So matrix anisotropy plays a lesser important role than these tectonic structures. Then the niche was excavated with a lot of parallel investigations, and one important investigation was optical televiewer logging. Optical televiewer logging was very important because we could verify the classification of fractures mapped on core. On the upper diagram here, you see a classification of fractures mapped on core. So you have excavation-induced unloading joints, and you have desiccation cracks because the cores dry out, and you have a lot of artificial joints which are caused by handling, which are caused by drilling, and then we have the tectonic shears. The classification of these different fracture sets on core is not always very clear, so it has been very important to compare this classification with what we can see in optical televiewer images. So on the lower part, you see now unwrapped images of an optical televiewer camera. So this is the depth along borehole, and this is just the unwrapped image. And you see a lot of important things. So you can see that, not on this figure, that some of the fractures which were classified as artificial joints in fact also occur in the borehole wall. So therefore they cannot be caused by handling, and most probably also not be by drilling, so they are natural in origin. And what you can also see, you have a lot of damage visible in these optical televiewer images, and the damage always occurs on opposite sides when you look into opposite sides of the unwrapped borehole. And you can also see that the damage starts at different depths in the borehole. And this damage, in fact, is related to what is called the hoop stress. If the hoop stress exceeds the rock strength, we start to have these breakouts. And if these breakouts do not occur at locations where the bedding is parallel to the borehole wall, then we can also derive stress orientations from the orientations of these borehole breakouts. These breakouts do not form close to the collar, which is here. And we assume that this is a region where the rock mass has been weakened due to damage prior to drilling of these boreholes and prior to getting these images from logging. So this is a zone of stress redistribution due to damage around the excavation, and this is in fact the area where you see the breakouts, where you had not much stress relaxation in response to the formation of an EDZ around the niche. This is a summary of the observed macroscopic fractures. So the niche-induced macroscopic unloading joints, which have been classified either as unloading joints 1 or 2, depending on the reliability with which we could interpret the core and the images. So red are quite clear unloading joints, and green are joints where we are not absolutely sure how they have formed. So you can see in this image that macroscopic fracturing caused by the excavation of the niche only occurs very close to the niche, not in a large distance from the excavation boundary. What is also very valuable is what we have gained from seismic borehole measurements. The seismic borehole measurements have been carried out with a probe that has a source and receivers in different distances from the source. And when we look, for example, at the compressional wave velocity calculated from the signal arriving at channel 1, we have a signal that characterizes only the very near surface around the borehole. If we look at channel 2, we have a signal that penetrated deeper into the formation, and we have even a deeper signal when we look at the response from channel 3. So what you can see on this right-hand diagram are repeated measurements of seismic properties in a borehole which has been drilled in the center of the niche. And what you can see here is that you have, for example, when you look at the compressional wave velocity from receiver 1, that you have a plateau somewhere around 2,800 meters per second, and that whenever a new log is measured after excavation stage has been completed, you always see that you have a first section of your log where your seismic velocity is significantly lower than this plateau. So this is in fact a representation of the damage in front of the advancing face, and this distance is between 20 centimeter and 70 centimeters. So this is the damage that occurs in front of the sequentially excavated face of this niche. We now compare this macroscopic damage and also the change in seismic velocity with stresses calculated with a very simple continual model. This model only looks into the elastic deformation, but we have a model which assumes isotropic conditions, and we have a model which assumes transversal anisotropic elastic conditions of the matrix. And in this 3D model, the Gallery 04 has initially been excavated, then what is called HGA niche, and then our EZB niche in different steps. So here we compare now the simulated stresses from this model, and what is shown here is only the ratio of sigma 3 to sigma 1, which is called the spalling limit, which has been identified as an important property for excavation-induced fracturing, or called spalling, in granite. What you can see on the other parts of this figure are the optical images. So this is an optical images which was taken a few days after the excavation of the niche, and this is an optical images which was taken many weeks after the excavation of the niche. And superimposed on these optical images we have p-wave velocities, we have the amplitude of p-wave velocity, we have shear wave velocity, the amplitude of shear wave velocity, and the ratio of p and shear wave velocity. So what you can see, this is just one example, this was done in all boreholes, that in this borehole we have in fact here macroscopic excavation-induced unloading fractures, and this is an area where you have a significant decrease in p-wave velocity and amplitude of p-wave velocity, and this also corresponds to a modeled ratio between sigma 3 and sigma 1, which is very low, which is in this range between 0 and 0.05. Then we see we have a first plateau in the seismic properties, which is shown here and which is also shown in the amplitude of the compressional wave velocity. And in this plateau we do not see any more excavation-induced fractures, so these are artificial fractures. And we don't see damage in the borehole, which only starts here, when we get to even a higher p-wave velocity amplitudes and also amplitudes of shear wave velocity. So from this we conclude that excavation-induced fractures, macroscopic fractures, indeed only form when this spalling limit or ratio between sigma 3 and sigma 1 is very low, that we have additional damage in this middle zone, which is not seen macroscopically, but it's seen on a reduction in seismic properties. And then we get, let's say, into the more or less undisturbed formation, where we still have, the initial stress conditions because the rock mass has not been weakened, and the response to these high stresses is damage of the borehole walls. So we can see similar patterns in other boreholes. I have not enough time to show you now the results from all these boreholes. This is a kind of summary of the response seen in boreholes drilled through what is called the north vertical plane. And what is shown on this diagram in sigma 3, sigma 1 space are the simulated stresses along the center line of all these boreholes shown in this vertical plane as a function of excavation stage. So these are the initial stresses along these boreholes, so clearly below the damage initiation. This is when the entrance to the EZB niche has been constructed, so also now all the boreholes do not really reach stresses which are above the damage initiation, and now we have fully excavated the EZB niche, and now you see that some boreholes really reach stresses which are in an area which is in sigma 3, sigma 1 ratio, which is very low. And in fact, a spalling limit of 0.05 has already initially been proposed as a condition for the formation of macroscopic fractures. And this is more or less also what we see. We see that in the borehole BZB8, which is this borehole, and in borehole BZB12, which is this borehole, we can just see macroscopic fractures at the borehole collar, and this here is the borehole collar, where the stress ratio is very close to what was already postulated for the formation of macroscopic fractures. And when you are more distant away from the excavation boundary, we still have some damage which can only be seen in seismic properties and which relates typically to spalling ratios between something between 0.2 and 0.1. This is a summary. This is a summary showing in cross-section and in plan view the observed location of macroscopic fractures and the observed, let's say, reduction in seismic property, which we interpret as a microscale damage of the rock mass. And outside, let's say, of this boundary, which typically is 0.5 meter from the EZB niche, we start to observe breakouts in these radial boreholes. So this is the summary. We have created a niche which has similar dimensions like a real high level waste repository tunnel. Unfortunately, this is only a short niche, so we also have 3D effects which we have not discussed in this talk. We carried out very detailed analysis of structures in 3D space and looked at the evolution in time. And the interpretation approach is mainly based on an integration of geological and geophysical data, which was complemented with stress from numerical modeling, which are very simple models if we consider the very complex, let's say, mechanical behavior of these clay shales. So, for example, we have not considered the non-linear behavior of the deformation of the opalinus clay. We have not considered pore pressure coupled deformations, which we are studying now in other PhD projects. The main conclusions are that rock mass heterogeneity, so not only matrix anisotropy, so tectonic shears play a very important role on the development of induced fractures, and we have seen that the level of damage can be approximated by considering the maximum and minimum principal stress ratios. A lot of this has been published. You can find these results and read them in greater detail in these publications. And many people have contributed to the success of this large project, and I really acknowledge all their contributions. Many thanks.